Alright, hello everybody. Today I'm going to be going, or in the video I'm going to be going over section 9.3, and this is dealing with what is called two dependent samples. Recall that section 9.2 was making inferences from two independent samples, and we called that unmatched pairs. And section 9.3 is about making inferences about two dependent samples. And this is what is called matched pairs. Or another name is independent samples. So, and again, the idea is that you have two samples coming from two separate populations, and if there is a way to pair the samples together or match pairs in both of the samples, or there's a natural pairing, that's what we call match pairs, and the samples would be dependent on each other. Some of the examples of this were taking measurements before and after, husband or spousal relationships, where you have data from, say, a husband and a wife. And we'll go through an example or two in just a moment, but first, to get some notation out of the way. So, what we're doing is we're looking at two populations of data that are paired in some natural way, and what you can imagine doing is, you have a first population and a second population. If you took the differences between each matched pair, that would be what lowercase d would represent. So d is going to be the individual difference between the two values in a single matched pair. Mu sub d, so mu, remember, is a population mean, and this is the mean value of all the differences for the population of matched pairs of data. Okay, so again, you have two populations of data, you match the pairs, in each pair you take a difference, so you're calculating a bunch of differences within each pair, and then mu sub d is the mean value of the differences, okay, for the entire population for each of those matched pairs. And then the idea is you're going to take a sample from each population, okay, and one thing you could do is you could find the difference of the match pairs in your sample data, and you could calculate the mean of that, and that's what d bar is. Okay, so you're going to have sample data, and the sample data will be paired, and if each pair in the sample data you take the difference and find the mean of those values, that would give you d bar. SD, so remember lowercase s stands for sample standard deviation. The subscript d is telling you that this is a standard deviation of differences for the paired sample data. Okay, and then n is going to be the number of pairs of sample data. Okay, or you can think of it as you have two samples, and n is the number of values in either of the two samples. Okay, so the idea here is you're essentially starting with two samples. Okay, you're coming from two populations, but since the samples are matched or are dependent, you are calculating the differences in each pair and thus creating a single set of data. Okay, so d bar would be the mean of those differences, SD is the standard deviation of the differences, and n is the number of pairs of sample data, and it's really the number of differences that you would be calculating. Now the test statistic, we're going to be doing hypothesis testing, okay, to test claims made about the mean of the differences between the match pairs and the population. And that test statistic formula is d bar minus mu sub d. Increase the size here just a moment. Scroll down. There we go. Okay, so d bar is going to be the sample mean of differences, and then you in the numerator here. And then you are subtracting the mean of differences in the population, And that's going to be coming from the null hypothesis, which we're going to talk about in just a second. And then you divide by the standard deviation divided by the square root of the sample size. Okay. If you look back at the one sample test of means and you look at the test statistic formula there, it's essentially the same formula. It's just that the notation has changed to fit the context of this particular problem. And of course, every hypothesis test, the first step is always to state null and alternative hypotheses. And the null hypothesis for a two dependent sample mean test or matched pairs test, the null hypothesis is always the assumption that the mean differences for the mean of the differences for the population of data equals 0. Okay. That's kind of like saying there's really not a difference between the two populations in terms of the data is concerned, that we're saying that the two populations of data roughly have the same mean, so the mean of the differences would be 0. And then there's three options for the alternative hypothesis. The mean of the differences is positive, negative, or not equals to 0. And remember, these would all lead to either a right tail, left tail, or two-tail test, respectively. One small example or thing to think about, okay, is if you were, say, doing a study of weight loss of a particular diet, okay, you might have a sample of weights before the weight loss or diet, and then you might have a sample of weights from after the diet. Okay, so that would be, two separate samples of data. You have data from before and data for after. And those would be naturally matched or paired because they're the weight, each individual, each pair represents the weight before and after for a single individual. Okay, so just imagine we're in that context. The null hypothesis would be saying that the mean weight loss, essentially, okay, because you're taking the weight from before or after, so you're subtracting your original weight from your new weight, and that would give you differences. Well, the null hypothesis would be that in the population, amongst all people who try that diet, saying that the mean of the differences is equal to 0 is saying that the mean weight loss is 0. Okay. So that would be saying essentially the diet has no effect. Okay, and then the three alternative hypotheses, you can take them this way, is the first two, the mean of the differences being positive. Now, depending on how you set up the differences, these first two right here are essentially saying that there's either the mean weight loss is positive, so that, in general the diet leads to weight loss, or one of them might say that there is actually a weight gain, so people actually gained weight using the diet. Okay, the mu sub d equals 0 would mean that there's no weight loss by taking the diet. Okay, and then I don't think the two-tailed test is as fitting in that particular context, but we'll see when those apply. Okay, so as with any hypothesis test, there are technically requirements that must be met to ensure the validity of the test, and this has never changed. Whenever we collect samples, we always want the samples need to be simple random samples. The sample data are dependent, okay, or they're matched pairs. There is a natural way to pair the two samples together. This allows you to take differences, okay, subtracting one of the values in the pair from the other. And just like in the central limit theorem from section 6.4, either the sample size has to be greater than 30 or the population is normally distributed. Okay, so here's an example. And I'll walk you through this. There's a way to carry out all the calculations by hand, calculating the test statistic. It's a t-test. If you look back at the formula for the test statistic, it is denoted with a lowercase t. So you find a test statistic, you use the alternative hypothesis and the test statistic to find a p-value, and then depending on the given alpha or the significance level used, you would compare your p-value to alpha and make a decision and formulate a conclusion. Okay, so the same process is still involved as any other hypothesis test. And what we're going to look at in this first example, what I was saying was, I'll show you how to do it by hand, actually calculating a test statistic and a p-value all by hand. And the other thing I can do is I can go on StatCrunch. I can show you how to enter the data into StatCrunch, have StatCrunch calculate these differences for you, and then have StatCrunch find. If you do it by hand, you can have StatCrunch find the mean and standard deviation of the differences. And the other thing you could do is just enter the sample data, enter the differences in the mean and standard deviation into like a little applet that's in StatCrunch, and it can calculate the test statistic and p-value for you. Okay, so I'll show you both methods. So in this example, we have a table. Okay, these are my two pieces of sample data, or my sample data. And these are the numbers of words spoken in a day by each member of 6 couples. It says, use a 0.05 significance level to test the claim that among couples, males speak more words in a day than females. Alright, so you have 2 sets of data, the words spoken in a day by males, and you have a set of data that's the words spoken in a day by the females in the couple. And remember, each one of these now, right, this is what I would be talking about when I'm talking about pairs. So I've got 6 pairs, right, and each pair represents a couple. Right, so I technically have 2 samples, a sample of males, a sample of females, but I can pair the 2 samples together. Now I have 6 pairs. And then what I'm going to do is, each pair, if you subtract, so what I'm going to do is, it really doesn't matter how you do this, it just, the choice that you make is going to change how you write your alternative hypothesis. Okay, so here we go. We've already had, I'll probably show you how to do this in StatCrunch as well, but I had StatCrunch already compute the differences for us. Okay, so again, I'm doing males minus females. That's very important that I chose and that you pay attention to which order you subtracted. So in the first couple, the difference would be 440. That means that in that couple, the male spoke 440 more words than the female did. Okay, so I took the number of words the male spoke and subtracted the number of words that the female spoke and got 440, and I did that for all 6 other pairs. Okay, now I'll go show you how to do this in a second, but what I did is I entered those 6 values into StatCrunch and had StatCrunch calculate the mean of those differences and the standard deviation. And remember, n is the number of matched pairs. There are 6 of them. So from those 6 values, I found the sample mean of differences, the standard deviation of the differences. Now, I'll get back to calculating the test statistic in a minute. Now, the null hypothesis is, what we're really doing here is we're testing the claim that males speak more words in a day than females. Okay? And then those 6 differences that I have up there, those are the differences in the sample. Imagine taking the differences amongst all couples in the U.S., okay, or just among all male and female couples, period. Okay, so if you took all those differences, the null hypothesis is saying that the mean of all the differences in the population of all couples is equal to 0. So that's the statement that males and females, speak the same amount of words in a day. That's what this statement right here is. Males and females among couples speak the same amount of words in a day. Okay? That's what that statement is. Now, the alternative hypothesis. Now, I'm going to have to erase this. The alternative hypothesis still uses the symbol mu sub d, the mean of all the differences in words spoken in a day by couples. Has to compare to 0. And you have to decide if it's less than, greater than, or not equals. So focus now. If you go back and read the question, this is the claim. We're testing this claim. Males speak more words. Okay, now look at one of these differences. Maybe just look at the first match pair. Notice that in that in that particular match pair, the male did speak more words than females, and the difference itself was positive. And you notice that that's actually the case for 5 of the 6 couples. So notice that the values of the differences are positive when males speak more words. Look at the mean of all 6 of those values. The mean of all 6 of those values is positive, 7,278.5. Well, if the mean of those differences is positive, and generally males speak more words than females in the sample, okay, right, notice the mean of the differences in the sample is positive. So we're trying to test the claim that it's also true in the population, that the mean of the differences for all the couples in the entire population is positive. Right? Okay. So you can compute the test statistic. Okay, and you might have to go back up to the other slide to recall a few things. But I'll just write them down again right here. Remember, D bar was 7,278.5. That was, we were just looking at it. That's the mean of differences amongst the sample pairs of data. The sample size was 6. Okay, and the standard deviation, I got that from StatCrunch by entering the differences into StatCrunch. 6,913.26. I plug that in the formula for the test statistic over here, and I get 2.579. Okay. And then remember, this was a right tail test, so you use StatCrunch to find the area above or to the right of that test statistic, and I actually get a p-value of 0.025. Okay. Now, in case you're doing this or using the t-table, but you'll be using the degrees of freedom is n minus 1. Okay, so back at the original statement of the question, there's a 0.05 significance level. So if you come back down here, remember with StatCrunch, the p-value rounds to 0.025. If you look at the t-table, it probably says that, I'd have to guess, if the table says the p-value is between 0.02 and 0.025, or the table would tell you it's between 0.025 and 0.05, but in either case, that p-value is less than alpha. Okay. When the p-value is less than alpha, okay, or when your p-value is low, right, meaning less than alpha, we will reject the null hypothesis. We always say that there is sufficient evidence in that case, and the original claim that we were testing was that males speak more words in a day than females. Just to remind you, since we did males minus females, the alternative hypothesis is saying, this is the original claim, males speak more words in a day than females. Okay. So we have evidence that the alternative hypothesis, or evidence to support the alternative hypothesis, that among couples, males speak more words in a day than females. Okay? Okay, so I may or may not actually make a video for this that I show you how to use StatCrunch. One thing that is tedious is it is kind of a pain when they give you two samples and you have to match the pairs and enter that into StatCrunch. Or, well, I guess you could just take all the differences, and you might have to use StatCrunch to get the mean and standard deviation of the sample differences before you find the test statistic. But it's not as bad as in the previous section. I think this is more doable by hand. Okay, now then the last thing you would do in this section is construct a 95% confidence interval for the true mean difference of words spoken between males and females in a couple. So the true mean difference of words spoken in a day between males and females. Now, what's the best estimate, like a single value estimate for a population mean of differences? You would start by estimating that with a sample mean of differences. So that'd be the mean of differences among the matched pairs of sample data. That'd be an estimate for the mean difference in words spoken a day amongst all males and females in a couple. And of course, every estimate comes along with some error. Okay, so the formula becomes you take the sample mean of d bar and you add and subtract. Now the formula for the error is t alpha over 2 times the standard deviation of the sample differences over the square root of the number of pairs or number of differences. Okay. We already calculated that it was 7,278.5. I didn't show you, but I did use StatCrunch to get that. I took my 6 differences and found the mean. Now, using degrees of freedom 5, if you go look in the t-table, under 95% confidence, you will see that you get 2.571 for t alpha over 2. So remember, there were 6 pairs of differences, or 6 differences. 6 pairs of sample data, but 6 differences. So the degrees of freedom would be 5. If I look in the degrees of freedom 5 row and the 95% confidence column on the t-table, you get 2.571. Then you multiply that by, we found the standard deviation of those 6 differences, the 6,913.26, and divide by square root of the number of differences. That gives you an error of 7,256.2, and you add it and subtract it from the mean of differences, and there is your confidence interval. Okay, so with 95% confidence, you estimated the true mean difference in words spoken in a day between males and females, amongst all couples, is between 22.3 and 14,534.7. Now, just like above, remember the differences were calculated by doing males minus females. One thing to point out, if you look at this, in your confidence interval, both estimates are positive. Right? The other way to write this is that the mean of the differences for the population mu sub d, I can do a better mu than that. There we go. is less than 14,534.7. Okay, this is right here. The true mean difference of words spoken in a day between males and females is mu d, and we estimated it was between those two numbers. Remember, to calculate d, the differences were males minus female words. So when the differences are positive, that means males speak more words than females. So you estimated that the difference in all the males minus females, the mean difference of all those differences, the mean differences amongst all males and females in couples was estimated to be positive. So what I'm getting at here is that the confidence interval has the same conclusion as your hypothesis test. Since both of your limits are positive, okay, that means that among couples, males generally speak more words than females. So, we are 95% confident the true mean difference in words spoken per day by males versus females in a couple is between 22.3 and 14,534.7. And this implies males speak more words in a day than females. Okay? And other than that, that's generally about it. On your My Math Lab, if you do it for extra credit, you're going to get there's two populations of data in which you take two samples from. There's a way to match the two samples together. They're matched pairs, or dependent samples. And then you go and you take the differences. Okay, you subtract one value from the other in each pair. Those differences become the data set. You find the mean and standard deviation, test statistic. Depending on if it's left, right, or two-tail, you find your p-value. Everything's essentially the same. If anybody has any questions, let me know. If you want to set up an appointment with me, I could show you how to use StatCrunch to do some of this for you, but I think it's easy enough to do by hand. I'll see everybody in class, and if you have any questions, let me know. Thank you.